Moving clocks run slowly, and moving things contract in the direction of their motion.
I'm going to also ask you to watch your language. And this is a plea not only to you in my audience, but also to some of my fellow teachers of relativity, because it's very easy to make statements that violate the spirit of the relativity principle. You've heard about political correctness on our campuses. You have to make statements that are in tune with the prevailing political norms. Well, I don't want to get into that. But I do want to ask you, and ask myself, and ask my fellow teachers of relativity to be relativistically correct in our language. And what that means is, when you're describing what happens to space and time, be very careful to avoid any statements that might suggest there is a preferred frame of reference, a preferred state of motion. Why? Because there isn't a preferred frame of reference, and there isn't a preferred state of motion. The Copernican principle has been expanded through special relativity to say that all uniformly moving frames of reference are equally valid places, situations to do physics. So avoid any statements that would suggest anything to the contrary. For example, in the last lecture when we put you in first the car, then the airplane, and then the spaceship, and we said, well, we both measure the same speed for light, and we said, how could that possibly be? And I simply hinted at the end of the lecture that it must mean that something is different about our measures of space and time. You might jump to the conclusion that, well, maybe the meter stick in the moving vehicle shrinks. Maybe something funny happens to the clock in the moving vehicle because the vehicle is moving. That's sort of the philosophy that Lorentz and Fitzgerald had when they suggested maybe the apparatus, the Michelson-Morley apparatus, contracts in the direction of motion. It's really this long, but because it's moving, it got contracted. What's wrong with a statement like that? What's wrong with a statement like that is the sense that somebody is moving and somebody isn't. Somebody, probably you think the person on Earth, has the right to assert that they're at rest and funny things are happening to clocks and meter sticks and space and time for the people who are moving. Nonsense. You in the moving spacecraft, moving relative to me, that is, you in the airplane moving past me at 600 miles an hour, you in the car moving past me at 70 miles an hour, because those motions are uniform, you have every bit as much right to claim that you're a place for doing physics. You have no more right to claim you're the right place than I do. We both have equal claim on doing physics and doing physics correctly. That's what the principle of relativity says. So don't think funny things happen to clocks and meter sticks or space and time because things move. The phrase "because things move" is a relativistically incorrect phrase. You're allowed to say, I am moving relative to you, or that clock is moving relative to this clock that I'm looking at. But you're not allowed to say, that clock is moving and this one isn't, and therefore funny things happen to that clock. That violates directly the spirit of the principle of relativity, which says all uniformly moving frames of reference are equally good places to do physics. And that means any uniformly moving clock keeps time just as well as any other uniformly moving clock. It's just as accurate. Clocks don't become inaccurate, quote, because they move. Because no uniformly moving clock has the right to say, I'm at rest and all the other ones are moving. What may be the case, and in fact is the case, is that different clocks moving relative to each other keep different time. But there's not one of them that can say, I keep the right time and all the rest of you are wrong because you're, quote, moving. Because nobody has the right to say, I am moving. I will even slip occasionally and use phrases that are not correct. If I ever say the moving clock or this is moving, what I really mean is this is moving relative to that. That's why it's a relativity theory. It says only relative motion matters. Lecture 3, we went over this with the Galilean relativity principle. Only relative motion matters. Statements about absolute motion are meaningless. They were in mechanics all along. They became so in all of physics with Einstein's special relativity. So everybody who's in uniform motion is in an equally good position to do physics. So let's now move on and see what actually happens to space and time in special relativity. We'll start with time. We're going to be talking a lot in the next few lectures about events. I just want to tell you what an event is so we make it very clear. An event is something specified by giving both its place and its time. For example, your birth is an event. It occurred at a specific place and it occurred at a specific time. Just to give the place, to say New York City, for example, is not sufficient to specify your birth. Just to give a year, 1960, is not sufficient to specify your birth. New York, 1960, that does it. An event is a place and a time. And events are the key things in relativity. So we're going to talk a lot about events. What I'm going to do now is give you a somewhat artificial seeming example that I hope will convince you of what exactly happens to time because of the principle of relativity being true. I'm going to imagine a device which I'll call a light clock. And here's a picture of a light clock, and you audio people have a picture of the light clock in your booklet. The light clock consists of a box, just a simple box. At one end of the box is a light source, and at the other end of the box is a mirror. And we're going to imagine a pulse of light leaves the light source, travels to the mirror, reflects off the mirror, and comes back. And we're going to be interested in the time interval between two events. And those two events are the departure of the light pulse from the light source and the return of the light pulse back to the light source after it's bounced off the mirror. If you will, this device is a clock, and that's the fundamental ticking. Tick as the light goes up, tock as it comes back. There's one period of the clock, and it keeps doing that. But we're just going to focus on one tick-tock of the clock, one outgoing light pulse hitting the mirror, coming back to the light source again. And the two events are light pulse leaves the source, light pulse returns to the source. And we want to know what the time interval is between those two events. So here's our light clock. Now, whenever you see pictures in relativity books or in my course or in anything dealing with relativity, it's crucial to ask yourself, and it's crucial to understand the answer to the question, in what frame of reference is this picture being drawn? Many relativity books fall down, I think, because they fail to tell you that, or sometimes worse, they'll draw pictures that are ambiguous. They're partly from one frame of reference and partly from another. And in relativity, things tend to look different in different frames of reference. And it's important to catch that difference. And I'll try to do the best I can. Sometimes I'll slip. But I want to tell you, whenever possible, what frame of reference I'm dealing with. So the picture I'm showing you right now on the left side of the screen is a picture drawn in a frame of reference at rest with respect to the light clock. What that means is we're in a frame of reference, we put this light box or light clock here, and it's at rest with respect to us. That's what I mean by saying this is a picture drawn in a frame of reference in which the light clock is at rest, or equivalently a frame of reference at rest with respect to the light clock. And I'm assuming that I've got a uniformly moving frame of reference. You might say, well, maybe it's at rest. Well, maybe it is at rest, but being at rest is meaningless. Maybe it's at rest on Earth. That's a particular state of uniform motion. Maybe it's at rest on Mars. Maybe it's whizzing through space at 99% of the speed of light relative to Earth. But as long as it's moving uniformly, that's an okay frame of reference. So I don't know exactly what the light clock is doing relative to Earth. Doesn't matter. The point is, I'm drawing a picture here from a frame of reference in which the light clock is at rest. And in that frame of reference, here's what's going to happen. The light is going to leave the source. It's going to go up and hit the mirror. It's going to return to the source. That's all that happens. And the light is going to travel a total distance which is twice the length of the box. And that's all we need to know at this point. What's the length of the light path for that light? It leaves the mirror, it leaves the source, it travels up to the mirror, it reflects off the mirror, it comes back and hits the source, and we know how far it traveled. It traveled twice the length of the box. No problem. Now, there are certainly plenty of other frames of reference that aren't at rest with respect to the light clock or light box, equivalently through which the light clock is moving. If I'm at rest with respect to the light clock and you go by me at 70 miles an hour in the car, then relative to you, the light clock is in fact moving. In fact, suppose you go by me in that direction, then judged from your frame of reference, the light clock is moving in the other direction relative to you. And you might say, oh, but it's really at rest. That's not relativistically correct. Both of those frames of reference are equally valid because they're both uniformly moving frames of reference, and no one has the right to claim they're at rest or not. So is the light box at rest, light clock at rest or not? It is in one frame of reference. It isn't in another. And that's just the way it is, and that's okay. So let's look at that second frame of reference and see what happens. So we'll look at the same situation, the light clock, the emission of the light, that's the first event, bounces off the mirror, comes back to the source, that's the second event. We're going to look at that sequence of events, at those two events, in a frame of reference now in which the light clock is moving to the right. That means relative to the frame in which the light clock is at rest, that frame is moving to the left, and therefore the light clock looks like it's moving to the right. It is moving to the right in that frame. By the way, a word to avoid, you might want to say, but isn't it really at rest? Again, avoid the word really in relativity. It's a very, very dangerous word because really implies there's some special case, some special frame of reference in which things are really the case, in which they're really right. The time is really this time. The length is really this length. This event really happened before this event. To use the word really is to sort of pin a specialness on one frame of reference, so let's avoid that. So here we are simply in a different frame of reference, a different place, a different state of motion that is equally valid for doing physics. It's a frame of reference which happens to be moving to the left relative to the first frame of reference I discussed, the one in which the light clock was at rest. And so in this new frame of reference, the light clock itself is moving to the right. So it starts out, there it is, and I got a little arrow to show that it's moving to the right at some speed. And to make this make any sense, that speed is probably pretty significant compared to the speed of light. We already expect that because we know that these relativistic effects aren't important at very slow speeds. You won't see these effects if you do this experiment and move the light clock at 70 miles an hour or 600 miles an hour. But if you move it at 80% of the speed of light, this will be a big effect. So what happens? The light flash leaves the source, and it travels straight to the mirror. But in this frame of reference, straight to the mirror means it travels like that, at an angle. At the time the light pulse hits the mirror is in a different location. The light pulse still hits the middle of the mirror. The same physical things have to happen. In one frame of reference, the light pulse left the source, it hit the middle of the mirror, and it came back. That's got to happen in the other frame of reference. There's no question about what happens. It's a question of interpretation about how long the intervals are between what happens and so on. So here we are halfway through the process. The light pulse has hit the upper mirror. It's in the process of reflecting off it. It comes back, and by the time it returns to the source, the light box is in a different place. Okay, now, there's nothing funny and relativistic yet. I could have described this all in old-fashioned classical terms. The light clock could be in a car which happens to be moving to the right, and the first frame of reference is the frame of reference of the car, and the second frame of reference is the frame of reference of an observer on the road who sees the car go by. And there's nothing unusual about this. These are two different descriptions of the same sequence of events from two different points of view, two different frames of reference. Here's the crucial point. In the second frame of reference, the one in which the light box is moving, notice the light path. The light path is longer. Why is it longer? It's longer because the light travels diagonally to get to the mirror, reflects, and comes back diagonally. It's a longer path. It still has the up and downness of the length of the box, but in addition, it has a component of its motion in the direction the light box is going. In classical physics, in old-fashioned pre-relativistic physics, we say, oh, well, that's okay because the light is actually moving a bit faster in the right-hand frame of reference because it has the motion of the light box imposed on it. And we could describe that in terms of the ether and so on if we wanted. But now we believe in the principle of relativity. The principle of relativity says the laws of physics are the same for all observers in uniform motion. All laws of physics, including the principles of electromagnetism, including their prediction that there are light waves, including the prediction that those light waves go at speed c. So what has to be the case? The speed of the light has to be the same in both frames of reference. And yet, in one frame of reference, the light is moving further than in the other frame of reference. This is where relativity comes in. Relativity comes in our assertion that the light moves at the same speed in both these frames of reference. That's what's going to give us all the trouble with time. That's what gave us the trouble in the experiment of measuring the speed of the light flash from the traffic light, too. The assertion that all these observers had to measure the same speed. Observers in both these frames of reference measure the same speed for light, but in the left-hand frame, in the frame of reference at rest with respect to the light clock, the path length is shorter. And we can conclude, in the left frame, we have a shorter path, we've got the same speed, and therefore the time between the events is shorter. In the frame of reference in which the light clock is moving to the right, we have a longer path, but by the principle of relativity, we have exactly the same speed c for the light, and therefore it takes more time. And that's simply the way it has to be. If you accept the principle of relativity, the very simple, benign-sounding principle that says the laws of physics, including electromagnetism and predictions about light, are the same in all frames of reference in uniform motion, then this conclusion has to follow. The time intervals between those two events are different in the two different frames of reference. Now you might say, oh, well, okay, this is just a peculiarity of this funny light clock we're using here. This is something that, you know, if I used a real clock, like this clock, that result wouldn't happen. But that's nonsense. We've made a clock. What's a clock? A clock is a device that accurately, repeatedly undergoes some kind of happening that is periodic, that occurs over and over and over again. In an old pendulum clock, that could be the swing of a pendulum once a second. In this light clock, it's the bouncing of the light pulse from the source back to the source. In this modern quartz clock, it's the fundamental vibration of a quartz crystal that vibrates 32,768 times per second. That's a power of 2 from 1 second, and when you divide that down with electronic circuits, you get a ticking every 1 second, exactly 1.0000 seconds. A clock is simply a device that undergoes a repetitive, periodic motion or change of some kind, and that light clock is a perfectly good clock. And what we are doing here is discovering not something about the light clock, or not something even about light, but something about time. The phenomenon we've described here is called time dilation. Time is different in different frames of reference. Clocks do not keep the same time when they're moving relative to each other. They're still perfectly good clocks. There's nothing wrong with the light box when it's moving. It's the same one. It's just looked at from a different frame of reference. It isn't keeping bad time, quote, because it's moving. It's keeping perfectly good time in either frame of reference. It's just keeping different time. Time dilation isn't about light. It isn't about light clocks. It's about time itself. Measures of time are simply different for different observers in relative motion. The time interval between two events is not an absolute quantity. It's something that depends on your point of view. We're going to have to give up the absoluteness of time and soon the absoluteness of space if we accept the simple principle that the laws of physics are the same for all observers in uniform motion.
You can see then why actually moving clocks run slowly.
Time is running slower on board the rocket.
Time for the moving clock runs slow.
When you read books about relativity, you will often hear time dilation described by saying, moving clocks run slow. There's two things wrong with that. It's probably grammatically incorrect. It should say slowly. But much more profoundly, it's simply not relativistically correct. And I'd like you to pause right now, turn off your VCR, turn off your cassette player for just a minute, and think about what is wrong with the statement, moving clocks run slow. Why is that statement not relativistically correct? Think about that for a few minutes. When you're done thinking about it, start up again and we'll continue. So what's wrong with the statement, moving clocks run slow? It implies there's something special about motion, special about movement, that there's somebody who's not moving, for whom the clock is right and doesn't run slow, and somebody else for whom, because they're moving, the clock runs slow. Nonsense. Nobody can say, I'm moving and you're not, or you're moving and I'm not. That's the whole point of relativity. Moving clocks run slow is an absurd statement. It's nevertheless used very commonly, including in physics books or books for non-science people about relativity, to describe this phenomenon of time dilation. One problem with the idea of moving clocks run slow is you might imagine yourself in a spacecraft whizzing past Earth with a clock. That's a moving clock, right? And the moving clock runs slow. So you might imagine, in your frame of reference, everything seems to have slowed down. You watch the hands of your clock creeping slowly, having your heartbeat slow. Nonsense. That frame of reference is just as good a frame of reference for doing physics in as any other frame of reference. Things have to seem perfectly normal in that frame of reference. If they didn't seem perfectly normal in that frame of reference, physics would be somehow different there. And the whole point of relativity is the laws that govern physical reality don't depend on your state of motion. They're the same for all observers in uniform motion. Things can't seem strange. Even if you're in a spacecraft whizzing along at 0.99999 the speed of light, everything in the context of that spacecraft, in your frame of reference, your heartbeat, your aging, all that seems perfectly normal. Time for you may be running differently than it does on Earth. We'll get to that in the next lecture, but everything seems perfectly normal. So what does time dilation really say? Let me describe what it says. Here's what it really says. It doesn't say moving clocks run slow. Instead, it says something a little more complicated. It says if I have two events, and I measure the time between them on a clock that is present at both events. Remember the light clock when it was in the frame of reference where it was at rest. That light clock, that same box was present at the emission and the return of the light flash. Okay, we're going to now replace that light box with a couple of real clocks. Okay? And so what does it say? It says something like this. It says, first of all, we're not going to say moving clocks run slow anymore. That's bad, relativistically incorrect. We're going to say a little more sophisticatedly, the time between two events is shorter when you measure it with one single clock that's present at both events rather than measured by two different clocks. So here's the picture. And this is the picture that should come to your mind when you think about time dilation. I've got two clocks, clock B1 and clock B2, and they're located at two different places. And I've got another clock, clock A, whose state of motion relative to the other two clocks is such that A will be present at clock B1, and then later will be present at clock B2. And the two events we're interested in are the first event, which is shown here, when clock A passes clock B1, and the second event, which will be when clock A passes clock B2. Now, you may be very tempted to say, oh, A is the clock that's moving. And I've got an arrow showing that indeed A is the clock that's moving, and later clock A will be above clock B2. And in that sense, it is moving. In the frame of reference of the clocks B1 and B2, and that's the frame of reference from which this picture is drawn. Remember, I asked you to always think about what frame of reference is the picture shown in. In that frame of reference, clock A is indeed moving. But that doesn't say clock A is absolutely moving. It simply says clock A is moving relative to the frame of reference in which the two clocks B are at rest. They're at rest relative to some frame of reference, the one in which they're at rest. They're at rest relative to each other. I've put them that way. I've glued them to the wall in that frame of reference. Clock A is moving relative to that frame of reference, but clock A isn't moving absolutely. Clock A has every right to say, oh, the clocks B are moving relative to me. I'm not moving. So that's why I don't want to call clock A the moving clock. Clock A is simply a clock that happens to be present at the two events. It's a single clock. Clock A is present at the event of clock A and clock B coinciding, and clock A is present at the event of clock A and clock B2 coinciding. Neither clock B1 nor clock B2 is present at both those events. And what does time dilation say? Time dilation says that the time elapsed on clock A between those two events will be less than the time as measured by the two other clocks. And that's crucial. It takes two clocks in one of the frames of reference and only one clock in the other frame of reference to do this measurement, to determine the time interval between the two events. Now, this is not a mathematically oriented course, but I do want to tell you the actual result of doing this measurement and calculating what the time differences should be. There's a little formula, and we will use this occasionally, and any of you who have had high school algebra and can use the Pythagorean theorem could easily go back to the light clock picture and look at those diagonals. Hint, diagonals have to do with the Pythagorean theorem, and you could calculate the time in the one frame versus the time in the other frame, and you would find that the time, which I will call t prime, that's the little thing after the t for time on the left side of that equation, the thing I call t prime, that's the time measured on clock A, the one clock that's present at both events. That time is the time measured on the other two clocks multiplied by a factor 1 minus v squared, square rooted, where v is the speed measured in terms of the speed of light. So if you're going half the speed of light, v is a half. And that number is always smaller than 1, and therefore t prime is always less than t. And we're left with the conclusion that time is simply not an absolute quantity. The time interval between two events is relative. It depends on your frame of reference.